to this company. So we did say that the design process was a process in which we engineers, when I say we, engineers apply engineering science, the knowledge of engineering science, the knowledge of mathematics in the creation of solutions to problems. Okay, so it could be products, it could be components, it could be a machine, it could be a process, all right? In the creation of all of those to solve or to meet an identified need. And we said that over time, design theories have been formulated, okay? And it was formulated because there was a need for a standard process, a laid down process that, if followed, the solutions developed would be robust, would be, there will be solutions indeed that they solve the problem, right? And so we said that there are different models that have been proffered since from around the 1950s and 60s, but all of them have the basic skeleton, right? And we identified the 8-step design process that we would use in this class. And we ran through them last week. We say you begin recognize the need, then you do problem definition, then you research, you ideate, you do detailed design and analysis, then you communicate your design idea, and then you create a physical prototype before you now run testing and evaluation. So we will run through these stage by stage and discuss. We did mention that the design process in general is not a one-man affair, right? It takes a team of different experts, people with different experiences, different knowledge bases, different expertise, who contribute, to the process to ensure that it is successful. And so it is not a one-man thing. At each of these stages, you will find different teams of different persons doing different things to ensure that the stages are successful in themselves. And then we also identify that these processes or these stages, some of them are not limited to the point where they are in the process. Okay? All right. We can follow these sequentially, one after the other. But some of the processes, for example, communication, there are 3 forms of communication. When we come there, we will define those. There are 3 forms of communication: oral, written, and graphical, right? And the communication happens across from recognizing the need, okay? When you want to empathize, we did talk about a little bit last week, and we'll talk about it a little bit more this week. You sometimes need to locate yourself in the vicinity of the problem so that you can understand it. And when you go there, you talk to people. Communication happens through all these stages. Is not only limited to the communication stage. But when you come to the communication stage, we refer to that stage there when you are generating your graphical representations of what you have thought of as the solution to whatever problem it is you have identified, right? And so communication happens across each of these stages. Research also happens at various points here. So it's not limited. So some of these stages will occur through the whole process. Some at different points in it, not just where they have been identified. We did say it's an iterative process, right? Which means that you can move, by the time you come to ideation, you might have to go back to problem definition to tweak something. Okay, you might have thought of it, oh, but this is actually not the problem. What you're experiencing in your either your thought process or the calculation stage, there's something that is not really working, and then you go back. So it is an iterative process. You can repeat certain steps again and again and again to fine-tune the development of the solution that you are working in. Okay, we've talked about different. So let's begin with the first stage in the process, the stage where you recognize the need. Okay. You do not create a solution to a problem that does not exist. Okay. It is in response to a problem you have identified that a solution is created. All right. So the purpose of this stage is to establish the ultimate purpose of your design process. That's what you do in recognizing the need. What is the purpose of the design process you are going to engage? You are developing something in response to an identified need. Okay? And so your need might be, a dissatisfaction you've experienced. It might be something that is not working well that you've noticed. And so at this point, we form a general statement that states the need we have seen. Okay, we don't give so much thought to, okay, so how will we go about solving it and all of that. No, we will do that at the problem definition stage. We'll talk about design approach and all of that at the problem definition stage. Right at this stage is just to identify and to form a statement out of which, when you now come to define the problem, you will define. And for example, Makurdi is terribly hot. So let's say where you are living, okay, one of the days you get frustrated because you are really thirsty and hot water is not cutting it, right? And you're looking for where to get cold water and you can't find. That becomes a problem. That's the problem. There's a need there. There is a need for cold water where you are. So an example of a general need statement is what we have put there. Makurdi is so hot and no shop is selling cold water in this area, right? Just state your need. So that's the essence of this. Now, let's jump to the problem definition stage. There are two stages under this stage, right? The first stage is to research the problem, because this problem definition stage is the most critical stage in the whole design process. Because if you do not define your problem correctly, you will go ahead and develop a solution. The solution you are developing, you develop it in line with the problem you have defined. So if you go and develop a solution, right, that does not actually solve the problem that you identify, you might develop a very wonderful product, you might develop a very wonderful machine, but you will not meet any need. That need will still be there. So it's important to research to find out what is the true problem. Okay? So many times what you are seeing and you think is a problem. So for example, now you to our statement that Makurdi is so hot and so no shop is selling water, right? What do you think could be the problem? Let me allow you to unmute yourself so that give me a minute, I'll soon take this away. So if you want to speak, just unmute yourself and tell me what runs through your mind when you look at this statement. Makurdi is so hot and no shop is selling cold water in this area. What could be the problem? Yes, anybody? You can just unmute yourself and speak if you need to
Good
talk.
morning, sir.
Very quickly.
Good morning,
Yes.
sir.
Morning.
Well, sir, it could be, to me, I see that could be one of the causes here could be for maybe no electricity supply. That could be one of the causes. And another cause could also be that there are no equipment that will maybe, if there's electricity supply, there are no refrigerators that will make use of the electricity in cooling water. So
right.
For me, these are two possible.
One possible reason, thank you very much, is that maybe there is no electricity supply. Did you say no or low? Because if it is that the whole
To
area
like no
is
electricity
not electric,
supply
it's not,
within
it doesn't have
Makurdi.
electricity, is one case. But it's possible that they have electricity, but there's poor supply of power, right? That's good. That's one reason. Another reason is that there may be no equipment. They may not have equipment to, you know, to cool the water. Yes, any other problem? Any other problem that you think? One more person
So I
quickly. We
don't
don't have
know.
time.
Good morning, sir.
Hello.
Good
Good morning, sir.
morning. Morning.
Uh, I think another issue should be poor management from the owners of the shop
Okay.
because they have
Uh,
recognized that they have poor equipment that cannot cool the water, but let me say they have refused to work on it because they feel customers have no other place to
Mm,
get water from that, like the only
mm,
option. So I
mm.
think poor management is also the reason why no shop is selling cold water in that
All right.
particular area.
That's good. Poor management. So it might be that the shop owners are just careless. And because there is
Yes.
no competition, they feel that they can do whatever they want. So you will find that there are multiple reasons, right, why a problem could exist. So if you just stay aloof and you just assume what the problem is, what you assume might not actually be the problem. So if, for example, it's even that the cost of electricity in that area, they told them that since you are a shop, you are commercial, we will bill you at this rate instead of what we are billing residential persons. So you will stand and say, we don't have quota because there's no power supply. And then you go and start creating a solution that is based on the absence of power supply, and you go and achieve it, but you discover that when you come, they will still not buy it because your product is way more expensive than what the public power supply is giving them. So it's important to identify what the true problem is. It's important. So this is where you carry out research. Are you following me? This is where you carry out research. This is where you ask questions so that you can understand what the real problem is. And there are two ways you can research. You can research from books or published content, and you can ask directly from your clients. If it's somebody that now employed you and say, please, I have this problem. Can you develop a solution to it? Or if it's just you, then you might need to go to the target market and ask questions. Sometimes you might need to relocate and live in the vicinity of the problem so you can gain understanding of the problem. You can understand the nuances. They say somebody who wears a shoe that knows where he bites, right? So you might need to put yourself in the environment of the problem so that you will understand it properly. And when you understand it properly, you are now able to define. Okay. So when we come to defining the problem, we are saying you say specifically what your design is aiming to do to solve the need that you have identified. So you are saying specifically the problem. And when you get to final year, this is what we usually call the aim. When you are doing your final year project, right? All your projects in final year will be to meet an identified need. So, and by the way, let me say, you better pay attention because when you come to final year and I'm running seminars for you how to go about your projects and write your project reports and all of that, I will not repeat this again. Okay? It will be expected that you will know that to do your project, you follow this same process. You identify a need, you define the problem. That's where, if we ask you to write your chapter one, your introduction, you're giving us the background to your problem. Okay? And you are giving us some of the information that you've garnered through research. But you will define the aim of your project. What is your project wanting to do? And the objectives. What are the things that if you achieve, you will meet the aim that you set out to meet. So problem definition is you specifically saying what your design process is going to output that will meet the need that you have identified. Specifics. And you must include all the specifications required to design the solution. Okay, what's a specification? A specification is a particular value or parameter that has been fully defined, okay, that determines either the shape, size, or properties of the design. Is that okay? So it usually would limit the designer. For example, now, if I came and discovered that, so we are now having this class online, not because we want to, not because we have decided to move forward in our educational. If something drove us, right? A problem. And what's the problem? What's the problem? Unmute your mic and speak. Why are we not in the class?
Sir, we can't hear you. Abi.
Give me a minute. Let me.
But the network is frustrating.
I think network is giving issues.
It's having issues with the network.
Currently, even the
You connected? Is it got slow? Can you hear me now?
Sir, we couldn't hear you.
All right, but can you hear me now?
Yes, sir. He started
All right.
having issues from when you were explaining on specification.
Okay, I will go back there. I had to switch networks.
All right, sir.
Okay, so let me share my screen again. So I was saying that we are having the class we're having online, right? Because of a problem. Is that okay? Because of a problem. So what is the problem? What has driven us to have this class online? Or you can unmute yourself and speak.
No
The absence of classroom.
Absence of classroom. Okay. Is that really the problem?
Yes, sir.
Okay. Somebody else will speak. Because in our mechanical building, there are empty classrooms. There's a classroom that is there.
But there's no infrastructures in it for us to have a classroom.
Good. So if you say absence of classroom, to solve the problem is to build classroom. True or false?
True.
So your first perceived need might not necessarily be the main need. So yes, we don't have a class, but the real problem is it because there are no classrooms? No. Somebody said facilities. What facility?
Chairs and board.
A whiteboard.
All right. So there is no sitting. There are no seats. All right. Seats, desks, and seats are no whiteboard. Okay. Now, if we now want to define our problem, we will talk about defining. Maybe we'll say we are going to construct tables and chairs. Okay. To receive lectures in the class. Now, if you say you want to produce tables and chairs, and you go to a carpenter and say, produce for me tables and chairs, I want to put it inside the building. And that's all you said. You have not given specifications. Okay? So the carpenter can decide to do big tables as if they are laboratory tables, right? Big tables. Or you might decide to do a table that is very tall because you have not specified. But if you say, look, I want these tables to be in such a way that the width is at most 0.45 meters so that we can fit in as many as possible. How long is a long cover notebook? These students are just going to write on top. So at most the width, right? The length should be in such a way that it leaves room on both sides of the classroom for people to pass. You are beginning to specify. You are saying how or what specific parameters should be. The height should be in such a way that when somebody who is averagely 1.6, 1.7 meters tall sits, they will sit in such a way that their laps are horizontal. Is that okay? Please give me a minute. All right, I can see that Oyeman is putting up his hand. Let me finish my thoughts and then you can speak. And so you will need to specify, oh, the height of the tables you should produce should be this. The seats should be attached to the writing tops and all of that. Is that okay? And all of that. So, Oyeman, ask your question. I thought Oyeman wanted to speak. I want to see how I will stop you guys. I told you not to
Your
write on the
mic went
screen
to mute,
because
sir.
it affects all of us. Yes, go again.
You went mute, sir. I don't know if it's my network.
No, I told you guys to give me a minute.
Okay, sir.
Thank you. Please, can you stop annotating on the screen? So don't touch your screen because if you annotate, it comes up on all our screens. Thank you very much. So those specifications are values or parameters that are needed to fully define your shape, your size, and the properties of your design, so that whoever is designing, when you go on with your solution, okay, you have a guide. You are not just free to do anything you want. Is that okay? So specifications, they lay down the scope of what you are doing. They lay down the specifications of what you are doing. So we also expect that you output a formal statement at this stage in the problem problem identification or recognizing the need stage. We don't need a formal statement. It's just a general statement of need, however you say, that captures what you need, right? But in the problem definition, we need a formal problem statement, okay? Because everything hereafter is hinged on that statement. Okay, so you must expressly state what the design is going to accomplish, and you will include the objectives and goals of the design. You will include the constraints and specifications of the design. You will also include the criteria that will be used to evaluate design. When you finish, how do you know that this is successful? How do you know that this thing has met the need? Is that okay? So what you state will in your objectives and all of that is what will be used. So when you come to final year and you come to defend your project, we will look at your aim and objectives and we'll look at what you are presenting to us. Okay? Do they reflect that those aims, we use those aims and objectives and your constraints and scope to judge, to assess, to evaluate whether your solution was actually a solution indeed. Okay? So For the problem that we defined earlier, okay, maybe before we get to an example of a problem statement, some of the criteria that you can use in evaluating your design, right, which are called design considerations, could include strength. Okay, you might want to state that, oh, one of the things you are going to evaluate your machine for is strength. Okay, it might be reliability. You want the machine to perform or to output the same value or the same performance every single time. That's what we call reliability. It might be something that has to do with thermal properties, right? It might be corrosion, wear, friction, ergonomics, cost, safety, weight, maintenance. You don't want something that is going to cost so much to maintain. It might have a very high initial installation cost, but maintenance is key for you. So all of these are various criteria. Okay, the life of how long that thing is going to live. Does it make noise? Is it stylish? Okay, the shape, the size. Sometimes people just want something portable. I don't want something that is very big. What they have is working, is solving the problem, but they are not comfortable with the size. They want something posh, something portable. It might be speed, okay, and all of those. So these are examples of criteria that you can use or you can state clearly when you are evaluating your design. So we said we identified that, oh, Makurdi is so hot and no shop is selling cold water, right? And we discovered that the problem is power generation, power supply, cost, cost of electricity in the area. That's why these guys don't have cold water. So this is the problem statement. We say design a smart and renewable energy-dependent cooling system for cooling drinks and preserving perishable food items for use in places with very hot climate like Makurdi City. Okay, and now we're specifying the cooling system should, one, be portable. So it should not be larger than 0.5 meters by 0.5 meters by 1 meter. Okay, but it should be scalable for bigger applications. So if we want it bigger, but for now, we want something portable, okay? Two, it should depend mainly on a renewable source of energy, but it can be hybrid. In case the grid is working, we can get power from the grid, but its main reliance should be on a renewable source of energy. Three, it should be made of materials that are readily available and easily accessed locally. Okay, we don't want the material that you have to send to China before it comes, or you have to send to Kenya or South Africa. All right? We want locally sourced materials. Four, we want to incorporate sensors for information harvesting and system control. All right? So our design must include sensors that will read for us the various parameters involved in cooling so that we can also control the system. Because once you say it's a smart, we said a smart, that means it should be able to receive inputs and run in a certain way. Okay? Any other specification you can think of very quickly before we make progress? Quick. Nobody is talking. I hope I'm being heard. Can you hear me?
Yes, sir. Yes, sir.
Okay. Any other
Sir,
specification you can think of?
aesthetics, sir.
Aesthetics. It should be visually appealing to the eye. Okay? You can determine the aesthetics. It can be a specification. If you want it in a particular color, or you want a limited color, the final outlook should be colors red, blue, and maybe ash or silver. Is a specification. So you know that when you finish, it should be a certain color. All right. Great. So that's what happens in the problem definition stage. You define specifically what your design process is going to be trying to achieve in order to solve the problem. Okay. The next step is the research stage. Okay. At the research stage, what you do is you gather the information that is needed to carry out the design. Okay. So you diligently look out for, and you please, somebody keeps touching the screen. Can you let me see whether I have a way of ensuring that nobody touches. Maybe I'll check my Zoom settings later. We don't want to tick in anything on the screen. Just watch, because whatever you do, we are all seeing it, right? Okay, so it's a stage where you seek very diligently, all right? Very diligently, the information and data you need. So the concepts, engineering concepts and principles that govern the problem, you go and look to gather them, to understand them. You also check, has anyone done anything to solve this problem before? What did they do? Okay, what was their result like? And why is the problem still existing if they attempted to solve the problem? Okay, so you go and gather information, you gather research, you gather data. If I need this kind of material, what are the materials available in this vicinity? By the time you go, you discover that, to have a cooling system, I will need materials that are insulators to heat insulators. And so you start checking what materials are available within my locality, because one of your specification is your materials must be locally sourced. And so you start researching. And we earlier said that you could research either by reading books or published content, or by asking clients, or by interviewing people. The target market, can ask them. We can ask people who are living in the area, what kind of materials are these? You bring your knowledge of engineering science, material science, to know, will this be a good insulator? Okay. If it's a good insulator, does it have flexural strength? Is it rigid enough for us to form it into something that can stand? Okay. A lot of information is needed. A lot of data is needed. Okay. And we had already mentioned that gathering of information is not limited to this stage. Okay. It keeps happening throughout all the other stages. But at this point is when you sit down to read. The product of your research stage is what we call your literature review. When you get to final year, your chapter 2, we dedicate it to literature review. Go and review the literature. Tell us the concepts that govern this thing you're trying to do. Tell us what has been done before, all right, in this area. Get us all the information that is required in building your solution. Okay. Our sources of information could include textbooks. Textbooks, particularly, we deal with engineering science concepts and knowledge. You could look at company catalogs if you are looking at different components, different things that you want to build into your solution. Or maybe they have a certain machine that does something that is quite similar. You want to understand how we operate. You look at company catalogs. You can look at technical reports from government-sponsored research and development projects, R&D projects, right? You can have technical personnel handbooks. There are handbooks on shafts. If you are going to build a machine, there are handbooks that have technical specifications. If you want to transmit this amount of power, and that's what we're going to do. After this, we'll go into design of shafts and all those other machine components, right? What should we look out for? What is the standard? You can look at patents. People that have already, developed products and machines that have patented to their names. You can go and look at the patents. You might gain information, you might gain understanding, you might see something that works there that you can employ. Okay, you can look at trade journals and magazines, and then you can engage with people, experts. There's somebody who is an expert in material science. You go and sit Professor Bams down. You say, Professor Bam, there's a material, pick his brain as a professor of, of material science and metallurgy, meta math. Sir, we are looking for, and he said, 5 years ago, some of my students worked on one material that is lightweight, but good insulator and very rigid. You can talk to experts who will share, their word of experience and knowledge with you to aid you on in research. Now, research is also quite important. If you do not research properly, if you do not research widely enough, you might go and design a solution that already exists. Right? You'd have wasted time, wasted effort, wasted resources to design something that already exists. And when you come out, someone say, I know now, this thing's already there. We've used it before. It doesn't work. Or you might go and design something that does not actually function properly because you didn't gather enough, knowledge around the concept. You did not understand properly how the problem works. Is that okay? There are problems that are faced in research. Number one problem is laziness. Laziness. And from my experience, you guys can be lazy. One, you cannot even read. You don't even want to read. So how will you know what is? Somebody said some time back that a colonial master said, if you want to hide something from a black man, where do you put it? You put it in a book because he will not read. You give it all the solution to what is suffering is inside a book. They gave you the book. He will not read it. He will say that book I go chop. Where is all of this reading going? And all of that. Laziness is a huge problem. If you want to solve problems, you have to be hardworking. Okay? You will read a lot. You will read a lot. And you are not just reading because, some of you, everything you do now is just because you have to do it. What is the barest minimum I can do to get the maximum marks? That's all you want to do. So you are not even building knowledge. You are not even building understanding. All you want is, lecturer say this one will come out, will come out. That's the end. You will never touch it. You will never touch it. Okay? Let's not be lazy. The second problem that people face is, where will I get information and how will I get this information? Okay, I struggle a lot with so many of my researches because some very nice papers that I see, we don't have access to them on this side. You have to buy. And our school is not subscribing to these journals. When I was doing my PhD, I had a lot of friends that we said, I need this material. And my own university there subscribe to them. So I will download and I downloaded materials for people. Somebody's trying to read the paper and they say, buy this amount. You sign in with your institution. They sign in with Federal University of Agriculture, Makurdi, and they say the institution not recognized. And then they will reach out. And I'll just go and I find it, I download it and send to them. Where to get information? How to get information is a problem. Sometimes it's not even that you know where to get it and all of that. It's how. You may not even know where. I'm looking for information on this thing. Who will I ask? Which kind of book will I even check? Is it textbook? Is it journal paper? Is it conference paper? Is there a regular publication that I can get it in? Will I find it online? Okay. The third problem is accuracy and credibility. Is not every, your generation is suffering from a lot of misinformation because everybody is now a content creator. Somebody sits and just says something and then it flies everywhere. I used to vex with some of my older fathers. Everything they see, they believe it. Somebody will come and say, if you mix this and this, you will get this. Somebody will do a video somewhere. This, then they will start sharing it. Solution to electricity. Somebody one day came and said, if you put this bulb on these trees, they generate electricity. Then they say, even this one, no, they will cut the tree and put the bulb on it and it will shine. And people say, what's that tree? Let's plant it. Misinformation. They did not tell you that they carry the rechargeable bulb that is charged, and all you need is to complete the circuit. And each of those trees are wet. Every wet thing is a what's it called now? Is a conductor of electricity. They didn't tell you. And so people go and start planting trees in their house that to generate electricity. Misinformation, credibility of information. And that's why in research, particularly academic research, we only recognize information that have been peer reviewed or published in reputable journals that experts in the field. You say, oh, I found on I designed this thing, I worked on this solution. It's a solution to this problem. Experts in the field will look at what you have done and they say, yes, it's good, or you publish it. Okay, that's why things like Wikipedia, we don't accept, academic research does not accept information from Wikipedia because anybody can edit the information. You don't know who is editing it. You don't know the source of their information, whether it's correct, whether it's not. Okay, so accuracy and credibility of information, there are several published papers that have been retracted because they discovered that the scientists, the people who published those papers, they forged results. And it's a drawback to our collective effort to move our well-being forward. Why will you say you achieved something when you did not achieve it? Why will you say these are the results? If you do this, you do this. Because you know what you should expect. You expect that, oh, this thing should fit this kind of curve. So you will press the values. When you run your test, you didn't get it. You will go and force your values. No, we don't work that way. Okay, so it becomes a problem. How accurate and how credible is the information that we are getting? Okay, you could also find very credible information, but you don't know how to interpret it. What are these people saying? What is the meaning of this graph? I remember when I started my PhD, I didn't know anything in my PhD was a what they call now a multidisciplinary work. Okay, I was working on a device that was supposed to use it ultimately it was supposed to be used in diagnosis of diseases, right? Ultimately. So I had three supervisors. One was in my department in mechatronics, one was from chemistry, the other was from cellular medicine. Okay? And me in mechanical engineering, I read, see papers. I started studying, I was supposed to use graphene. The first 2 weeks I was using to read one paper, I said, God, if this is how it's taking me, this is how long it's taking me to read one paper. How many papers will I read? And in 3 months' time, I was supposed to present my proposal, a robust proposal of what exactly I was going to do for the next 3-4 years of my PhD. So information interpretation is key. Okay, and the more and that's why for you guys, when we teach you in classes, we introduce concepts to you and all of those things so that you will build understanding. In material science, they teach you people the stress strain curve. You know the point of yield. You know where fracture will happen. You know where linearity becomes non-linear when you leave the elastic region. All of those things. If you don't have that knowledge and somebody has carried the material and tested it and it gives you a stress strain curve, you can't interpret it. You look at it, you say, stress strain curve. So what is the information you are getting from it? At what point will this material fail? How much can we load it before it leaves the elastic region? Can you interpret, can you extract information from what you are gathering? You carry a paper, the person is talking jargon using the technical language in the field. Do you understand it? That's the problem. Okay? And this problem for you guys, if you really, really are an engineering student, you should understand some of these concepts. Okay. Now the next problem is when do you know that you have gathered enough information? because you can spend all the time just gathering information. You are not going to gather only, you will need the information to develop the solution that you are trying to develop. So when do you know that I've gathered just the right amount of information needed for me to, it's a problem. And that's why when you are early in research, you have supervisors. That's why all of you have allocated you guys to mentors who will become your supervisors. And you are expected to build a good working relationship with them now so that, and when the time comes, it's easy for you to interface with them. That the ones who will guide you and say, okay, you have gathered enough. Now, what about this information? Go and find out about this. You will need this to do this later. Is that okay? And then how do you apply all the information you've gathered to your current design? It's a problem. Okay, you can gather all the information and then not know how to apply it. And then there's a huge issue of plagiarism. Plagiarism is when you present an idea, you present a work that is somebody else's work without acknowledging them and without acknowledging them in the correct format. So it is looked at as if it is your idea. You have plagiarized somebody. Okay, and it's a huge issue. There's a lot on when you do when you create content. There's one of my girls that was creating content the other day, and I asked her, I said, what happened to your content creation? She said her page had to be closed down because she infringed somebody's copyright. Plagiarism, copyrights, all of these things, intellectual property rights, they are all about you making sure that you acknowledge somebody's idea. You say this thing is this person. And that's why when you start writing your literature review, there is what we call citation, referencing. Where did you get this information? Okay, it helps us know that it's not your information. It helps us acknowledge the source of the information and give them the due that they are worth. When you now work and out of your design, you generate your own data, you can now publish it and it becomes yours. That's why people go to patent. Somebody creates a machine that does something that nobody has created before. They quickly go and patent it. Okay, so that the commercialization of that is protected. Any money made out of that, they will not miss out on it. They will have their fair share of their dues. So plagiarism is a serious matter. Maybe when you get to 500 level, and I'm taking you in your seminars for project writing, I will talk about this a lot more. Again, I'm asking you not to touch your screen so that we don't have all these lines on the screen. Great. Any questions so far? Anybody has a question so far before we move on? Okay, silence means that you don't have any question. Can I check that you are hearing me?
Yes, sir.
We can hear you. Yes, sir,
Thank
we are
you.
hearing you.
I
Okay.
hear you very well, sir.
So let's move to the next
And that's
stage. The fourth stage in the design process is the ideation stage. Okay, ideation comes from idea generation. Ideation, the generation of ideas, of concepts. Okay, and the ideation stage itself has two sub-steps or sub-stages. The first is the concept generation stage. The second is the concept selection stage. This is where, after researching and gathering all the information, you now sit down and say, okay, I need a concept for my solution. For example, the fridge, we talked about this, well, let me not call it fridge, the cooling system. You have said, oh, you want to develop a cooling system, and so you have done a lot of research. You have looked at thermodynamics, you've looked at refrigeration and air conditioning concepts, you've looked at insulators, then you've looked at various cooling systems that people have designed. Okay, what the advantages are, what their disadvantages are, their basic operational procedures, and all of that. You've gathered all that knowledge. Now, in the ideation stage, is when to sit down and say, okay, for me now, I'm looking for a smart, renewable energy dependent cooling system, but could be used in hot places. It's very important. because in very hot places, your temperature gradient is higher. Your system has to do more work to cool down your content, right? Because if you find yourself in very cool environments, their cooling systems don't work very hard because the temperature gradient is not much. Okay, it's like pushing a car up a hill. If the hill is not slopey, it's not too up, you will push easily. But when the difference in temperature is high, it's like you are pushing a vehicle up a very steep. You will require more work. So, how should your system be? Are there specific things that the shape of your system will impact on the performance of your cooling system? This is where ideas begin to fly. Maybe it should be a box. Maybe we should have a fridge that opens from the top or from the side. Maybe we should have a fridge or a cooling system that does this. Idea generation, concept generation. So this is the stage where solution ideas are generated. Okay, and this is where creativity is very, very important. In fact, it's the most creative part of this whole process because you are required to be creative, to think outside the box, to think through things, to conceptualize, to bring out ideas and concepts on how to solve the problem. Okay, so at the concept generation stage, we are really, really just concerned about generating as many plausible solutions as possible, as many workable solutions. At this point, we are not really bothered about how great the idea is or how rubbish it is. No, all we want to do is to generate. So what should this cooling system be like? Just generate ideas, as many as possible. Your idea could be hinged on different material type. It could be hinged on form and shape. It could be hinged on how you intend to cool. Do you want to cool using refrigeration? What do you call those things? Refrigerants? Do you want to cool using something else? Ideas. Just generate ideas. Okay. And we say that this stage is preferably done by a team. When you want to generate ideas, sit a team together. So you discover that most of these companies that do stuff, they have people who they identify people who are creatives, who have great ideas. They take them on a retreat, on a vacation somewhere, cool place. They are not bothered about food. They're not bothered about what your own is. Just generate ideas. So if you are your creative juices flow the most in the morning, by that morning time, nobody's disturbing you. They just settle you down where you will enjoy. Everywhere is peaceful and calm so that your mind is working and generating ideas and thinking out of the box. This stage is preferably done by a team. Now, there are a few concepts that are used, a few approaches. In fact, there are many of them, but I will just talk about 3 or 4 here. Okay, you can go and look for others. One method is the method of adaptation or analogy. So if there is a field that has a similar working principle as your field, and then you check, so this kind of problem is similar to that problem in that field, and that is how they solve that problem. You can adapt. Okay, for example, water flowing through pipes in a house, water supply in a house, is analogous to electricity distribution in a house. Your electric wires can be looked at as your pipes, water pipes. Your switches can be looked at as your taps, your tap heads, right? Your battery can be looked at as your water tank. Okay, similar fields. You say, oh, so I have a problem of this in my electrical wiring. How is that problem solved with the distribution of water in a building? And then you take that solution and adapt it to say, okay, let's adapt it. So now in this case, instead of that water pipe had 3 pipes coming in. That means I need 3 different sources of electricity coming into this place. What did they do there? What can I do here? How can I modify that solution in that field to fit this one? That's one method of generating solution. Another is brainstorming. Okay, this is where you have a group of persons that does suggest solutions to a problem as it comes to their mind. You are brainstorming, you are storming your brain. Anything that comes, just note it down. No judgments, no criticisms, no checking which one is better. No, because the more the ideas, the better. Okay, so you have a lot of persons. Now you want to solve the problem to our classroom problem. Call yourselves together. What can we do? Mo do like this. Mo no do like this. Mo do like this. Mo no do like that. Somebody no, just generate ideas. Bring the ideas together. The aim of the next sub-stage, the concept selection, is when you now, what's the English I'm looking for? Objectively, without sentiment. It's not about who brought what idea. And when you are working in teams like this, you do not allow sentiments to override. Why you are not taking my idea? No, you don't know everything. Objectively, if somebody's idea is better than you, acknowledge it. Guy, that's a great idea. Your idea is more workable than my own. Throw yours out the window, right? Concept selection will come to that and will show you a systematic way of doing that. Okay, so you have brainstorming as one of the techniques. Then you also have functional synthesis. Okay, this is where you divide your overall system into subunits, subsystems. This system is supposed to do this, so you will design it based on its function. What are the requirements? It is meant to pump water, it's meant to push water. Water is meant to flow. For water to flow, this must happen like this, like this, like this. You will look at the functional requirements and use those requirements to create the individual subunits that should work. Then when you finish, you now combine all the subunits into a single workable unit where all the functions are synthesized. Okay, that's how machines work. You have various different moving parts, various things doing different issues. This morning, as I was coming, I was late because my car stopped. Okay, started jerking. And what was the problem? The alternator was not charging the battery. And because it was not supplying that required power to all, vehicles now are very, very electrically inclined. Okay, the nozzles are controlled electrically. Sometimes you different things. So once your electrical system has a problem, your vehicle will not function properly. Once one subunit. So in designing solutions, you might want to break it down into various functions and look at the functional requirements of every subunit. That gives you an idea on what it should look like. In fact, it will govern, it will guide, the ideas that you generate. Other techniques include mind mapping, storyboarding, reverse thinking, okay, 6 hats, and all of those. 6 hats is a very beautiful methodology where and each of the hats have colors. Okay, there's black, there's white, there's red, there's green, and each of them have scenarios. You take position. Okay, the white is a neutral position, right? Let me take a neutral position to this concept, this thing. If I'm a neutral person, how will I think of this problem? How will I solve it? Then you take a black position. Black is if I don't want this problem to exist, something. So you wear different hats and think through them. And then when you do that, you are able to think round, you identify pros, cons, you identify advantages, disadvantages, you're able to generate a very robust solution. Great. Now, assuming you have now generated a number of you have generated a number of ideas. How then do you now select? Okay, and this is what concept selection stage is about. Okay, you evaluate each of your solution ideas, right, in the light of the design criteria or the considerations you've specified. So if it's a cooling system as we've designed, you now carry all your ideas. Is it smart? How much dependent is it on renewable energy? Is it portable? Right? What again? All those other specifications. You now look at each of your solutions, right? And you will compare them to those criteria to determine which of them is the best, which of them is the optimal solution for the problem. And because some of these criteria can be, they are not, they are qualitative more than quantitative, okay? There is a very major tool that is used, we call the decision matrix, to evaluate, to check so that you can add, you can put values. If you have numbers to things, it's easy to tell which one is more. You compare the numbers. Whichever is highest is the best. Okay, so this is an example of a decision matrix, right? And let me bring up an Excel sheet so that we will do it together and we'll see. Are you following me? Is everybody with me?
Yes, sir.
Okay, that's fantastic. Give me 2 minutes. This is AME 403 machine design. Oh. Where is my decision matrix? Okay. So let's assume somebody wants to design a crane hook. Do you know what a crane hook is? Does anybody know what a crane hook is? Who knows what a crane hook is? You must have done it. You did drawings. I'm sure you must have drawn a crane hook at some point.
Like a big jack.
Yes, sir. Like a jack.
That lifts out of motor.
To lift something. Yes,
That
sir.
lifts heavy stuff, right? So the
Yes,
end
sir.
point,
Yes,
that
sir.
hook, where's my hand? That hook that bends like this, right? That's
Yes,
what we're talking about. So these guys want to make their crane hook, and they've identified 3 different solutions, 3 methodologies, and that's what we'll look at shortly. So let me quickly share my, where's the Excel sheet? Okay. So you see that they want to make a crane hook. Can you see my screen, everybody?
Yes, sir.
Yes, sir. Yes, sir.
Great. So they've identified 3 methods. One is to use welded plates. So they buy metal plates, they cut them and weld them together to form the hook. The next is to use riveted plates. Riveted. So instead of welding, why don't we rivet those plates together? Then the third option is to cast the hook. We build a sand mold, we melt the metal, pour it in, and cast the hook. So they're like, these are all workable ideas. Which is the best? Then they look at their criteria. What is their objectives? What are their design criteria? Material cost, manufacturing cost is important to them, manufacturing time, the durability of this material, the reliability, and the repairability. What's the difference between durability and reliability? Durability talks about how long will this thing last. Reliability is about performing in the same way again and again and again. Something can be reliable but not durable. So you say you want the crane to lift 1 ton, 1,000 kilograms of cement, right? And every time you use that crane, it will always lift 1,000 this thing at every time. In the same way, it can lift it up at the same velocity and all of that. That's reliability. But how long it does this is the durability. Repairability is whether if it malfunctions, if it spoils, can we repair it? Okay. Now, when you have this criteria, not all of them have the same importance. Okay. Because maybe the problem you are trying to solve is heavily dependent on cost. So the existing solutions, people are not using them because they're expensive. Then cost, which is defined by material cost and manufacturing cost. Okay? Material cost and manufacturing cost become very, very important. So even though, yes, you might want your crane hook to be reliable, but cost is the major thing. So we now have, you will assign, okay, you as the designer, you know which of these objectives is most important to you. You will assign what we call a weighting factor relative to one another, which one is the most important. And all your assignments should all add up to one. So when you look at these guys' weighting factor, which one do you think is which of these objectives is most important to him?
Reliability.
Reliability, right? Because it's taking 30% of the whole weighting factor. The guy is more concerned about reliability. I want this thing to perform exactly the same way every time. That's important to me. I don't want to compromise it. So 0.3. Then which one is next important? Which one is the most important after reliability?
Manufacturing cost.
Manufacturing costs. I don't want to spend time I don't want to spend too much at the manufacturers, right? Then durability and repairability, they share the same level of importance. Then after that, material cost, manufacturing time is not the problem. You want to take 3 days to make it, no problem. So far as it's going to be reliable and the cost of actually making it is not high. So you see that there is a weighting factor. Please follow me very, very, very carefully. There is a weighting factor, right? So we will, when we come to applying scores, this weighting factor will come into place. Now let's look at material cost. What's the unit for material cost? Is in Naira, Abi? Naira, that's how much. That's the unit. Manufacturing cost is Naira. Manufacturing time is hours. How many hours? Durability is experience. Experience will tell you how long is in years. Reliability, we determine that by experience. Repairability is also by experience. Okay? But let's take material cost, for example. If a material is more costly than another, which one would you prefer? Is it the one that is higher in cost or lower in cost?
The one that is lower in cost.
That is lower in cost. So your preferability, look at my English now. Your preference, your preference is inversely proportional to the cost. You would prefer a cost that is lower in value. So when we are comparing these things, the lower the value, the more attracted we are to it. All right? So we want to give the highest score to the one that is least expensive. Are we together?
Yes,
follow
sir.
Follow me. Aha. So you can decide to have your scale. You can do a scale of 1 to 5. You can do a scale of 1 to 10. Whatever scale you choose. You just know that for material cost, whichever one is the cheapest is the best for you. Okay? Now, so let's check. They discovered that to get the materials to do the welded plates, how much is the material? 250,000 naira, right?
Yes, sir.
When they come to riveted plates, because the same plates is what they use, it's just how they fix, how they fixate them together that differs. So for riveted plates also, the material cost is what? 250,000 naira. Yes. When they come to casting, the little metals that they are going to buy to heat, to melt and cast is going to cost them how much?
220,000 naira.
220,000 naira.
Yes, sir.
Which of these three methods wins so far as material cost is concerned?
Cast hook.
The cast hook.
The cast hook wins, right? So what we are going to do is we are going to give a score of 10. We are going to give a score of 10 to the cast hook. Is that okay? Are you following me?
Yes, sir.
Yes, sir.
All right.
Yes, sir.
So how do we now get the score for the riveted plates and welded plates? That's where our proportionality knowledge in mathematics comes into play. Okay? If a score of 220,000 naira is giving us a score, a cost of 220,000 naira is giving us a score of 10. What will be the score when the cost is now 250,000 naira? Noting that your score is inversely proportional to the cost. Okay? And so if you introduce a constant there, you will see what I've written in this cell here. The cost, the material cost, equals a constant value divided by what? The score we give it. So we are saying, in essence, that your cost is inversely proportional to your score. What that means is that the higher your cost, the lower the score we will give it. But the lower your score, your cost, the higher the score we would give it. They are inversely proportional. When one is rising, the other is going down. When the other is rising, the other is going down. Is that okay? So we have this equation now that we can use. So we take one of these instances. In this instance, we know the cost and we know the score, right? So if we look at this equation, we know the cost and we know the score. And so if we look at the next cell, it means that the constant value we're looking for is a multiplication of these two costs. Of the cost and the score. So K for us is going to be 220,000 naira times 10. Please, have you followed me up to that point? Somebody is raising their hand. Who is raising their hand? Oh, was it my hand I raised myself? Why is my hand raised? I did not raise you. Let's lower the hand. Okay. Please, have you followed me to that point? Because once you get that principle, is the same throughout. Okay? We check the relationship between how we are scoring these things and their magnitudes. The lower the cost, the higher the score we give it. That's inverse proportionality. If we make it an equation, we introduce a constant. So cost equals that constant divided by the score. The constant is the cost times the score, right? And for us here, and that's what I do in Excel, if we say this equals 220,000 times the score 10, what's our constant? Our constant is 2,200,000 naira, right? So if we now want to know the score using this equation, it means that the score for a given magnitude of the material cost is the constant K divided by the cost. Is that okay? So when we want to know this score here, we will take this 2,200,000 naira and divide it by the cost we're now dealing with. That will give us the score that the riveted plates we have, which is the same as that. Okay, so I'm going to just do an equation in Excel here that we do that. So that equation says that what is in this cell, the score, equals the constant, which is the cost times, oh, that's not the one I want, equals the cost for the cast hook, which I already know, times the score that I've given it, divided by the cost that I have here, okay? And that will give me my score. Did you follow me?
Sir, please come again.
Yes, sir.
Okay,
Sir,
let me
please come
walk
again.
through this again. So we said, let me delete all of this. We said that our cost is inversely proportional. Where is my insert? Where's my symbol? Oh, sorry about that. Can you still see my screen? Insert symbols. I want inverse proportionality. Inverse proportionality sign. Where's my Greek? Oh dear. Special characters. Symbols. Cambria math. All right. Subset is Greek. Where's inverse? Give me a minute, let me find it. I'm looking for the proportionality sign. One that's almost like half. Subset is mathematical operations. This is it. Okay, insert. Good. So my cost, Romanos, let me finish and then I will take a question. My cost is inversely proportional. So 1 over the score. That's what I have. Okay, so what that means is that if my cost climbs, what happens to my score? My score will be lower. The higher the material cost, the lower
the score.
The score. Okay, I can convert this into an equation. This means that C, instead of this proportionality sign now, what will I have? Equals.
Equal to.
Right? And then I introduce a constant, what? K.
K.
That's basic mathematics. All right? And from this equation, I can tell what K is. K is C times what? Times S. Agreed?
Yes, sir.
Yes, sir.
Yes, sir.
So what that means then is if I want to know the score for a given material cost, the value for the score will be my constant K, which is now what? Cost 1 times the score I gave that one, cost 1 times score 1, divided by the cost that is, so if I will call this score 2, divided by the cost associated with score 2. Do you get it? And let me put a bracket
Yes, sir.
here. We can put a bracket here. All right. So since this is Excel, I just put those values. Move you up. I just put those values inside my equation and it solves them. So I'm looking for score for 250,000, but I have a method that has both its score already and its magnitude. 20,000 naira gives us a score of 10. Now, for the value, you are seeing 2 because I've automated this already. Because when you multiply 10 times the weighting factor 0.2, what do you have? 2. Okay? So let's see. What then will be the score? If 120,000 naira gives us a score of 10, what will be the score for 150,000 naira? So this score equals, no. Are you hearing me? It's giving me a crash report. Can everybody hear me? All right, that's fine.
Yes, sir.
So this score, the score for 150,000 equals the cost for the riveted plates times the score that we have given it, which is 10, divided by this 150,000 naira that we're considering. So what's the score for 150,000 naira? 8, right? And then its value, because manufacturing cost is more important than material cost, its value is 1.6, right? Good. Let's find out for this one. Now, when you come to casting the hook, it's more expensive. So you discover that getting materials is cheaper, but it has the most expensive material cost, manufacturing cost. So what will be the score? Score will equal this times this divided by its own cost. And that gives us 5. So already, And the beauty of doing this in Excel, you can see how the individual these things change with time. When we started with manufacturing cost only, it looked like cast hook was the best method because it had one, all the other had 0.88, right? Now that we've added manufacturing cost, you can look at the total down here. Okay, the cast hook is already underperforming. It was leading the race at first. Now it has dropped because of the manufacturing cost and because of how important that is to us, right? So far, based on material cost and manufacturing cost only, riveted plates seem to be winning. It seems to be the best option. If those are the only two things you would have considered, then we would have gone for riveted plates. But that's not the only criteria. Let's look at manufacturing time. Manufacturing time is has a weighted factor of 0.1. Is the least important to us, but it's still important, right? So in hours, welded plates takes a whooping 40 hours to do. Riveting takes 25 hours. Casting takes 50 hours. Again, what's our preference? Is it the more the hours, the better, or the lesser the hours, the better?
The lesser the hour, the better.
The lesser the hours, the better. So automatically, again, riveted plates gets a 10, right? Because it's the least time that is available is used. So we will do the same thing to find the score for welded plates that is taking 40 hours instead of 25. So we say the score we give it equals the number of hours it takes to rivet the plate times the score that we give it divided by the 40 hours that we're now looking for the score for. And that gives us a 6.25 score. Let's go to cast hook. Cast hook is just going down and down and down. The score for cast hook equals 25 times 10 divided by the 50 hours it's taking. And that gives us a 0.5 value, a cost of 5, right? I mean, a score of 5 and a value of 0.5. Okay? So again, you see that all the two others are leaving cast hook. By the time you look at material cost, manufacturing cost, and manufacturing time, riveted plates is leading. Okay, let's talk about durability. Based on experience, we went and spoke to people who are experts in using crane hooks that are welded, riveted, and cast. And they say that for durability, welded plates are great. They last the longest. Riveted plates are okay, they are good. They are good. Cast hook is also good, right? And so we have a scale here, right? If we are using just based on experience, the highest is great. After great is what? Is good. After good is okay. Then fair. Then poor. On a scale of 1 to 10, that means great. We can give great 10, right? Since there are 5 of them, good will be what? 8. Okay will be what? 6. Fair will be 4. We can give poor 2, right? So this one is very easy. Once you have this scale, it's easy to plug. And in fact, all the 3, these things down here, it's easy. We don't need to calculate. We just plug. Great is 10, right? Good is 8. Good is 8. Good is also here. That's 8. Great is 10. Okay. Okay is 6. Good is 8. Great is 10. Fair. Fair is 4. Okay. So when we finish now, based on this criteria, based on the objective criteria that we have, you will see how each, and also based on which of these criteria is most important to us based on the weighting factor. It is clear that which option is the best.
Riveted plates.
Riveted plates is the best option. This is not sentimental. This is not because I have somebody that does riveting, so I want him to get the contract. This is not because the man that is going to weld, I don't like him. objectively, we have put down our criteria, we have assigned, we've put down all the values, we've done them objectively. There's a science to this. Riveted plates is the best option when you combine material cost, manufacturing time, durability, reliability, and repairability. It's the best option. It scored 9.58. Welded plates scored 8.25, 205, and then cast hook had was 6.1. So we go with riveted plates. Now, this is important because if something happens along the way, you were coming and the only man who does riveting in your village now died, will your project stop? No, it's easy. Okay, since riveted plates is no longer possible, what was the next best possible welded plates? Now, if you come to pitch this to somebody and they say, no, cast hook is the best. Cast hook is the best. Why did you not use cast hook? You say, just because I know this is what we lecturers, we like doing when you are doing your project defense. We ask you questions to see whether your solution was a well thought through solution. Did you consider others? So someone will come and say, no, cast hook is the best option. How much is the material for cast hook? Brother, you will spend 220,000 and you want to go and spend 250. Then you stand there and you're looking like Momu because you did not use objectivity. But if you say, no, sir, look, there were 6 criteria that we're working for. We did not only look at material cost, we also considered manufacturing cost, manufacturing time, durability, and all of this. And based on this, we can show you our decision matrix. Based on this, riveted plates was the best option. It has the best combination. And then your decision is scientific. Your decision is statistical. Your decision is objective. It's not based on sentiments. Did you follow me to that point?
Yes, sir.
Yes, sir.
All right.
Yes, sir.
So please know how to do this thing. It can help you when you come to choosing materials. You have many possible materials for a given work that you are going to do. Look at what am I looking for in this material. I'm looking at thermal insulation. I'm looking at durability. I'm looking at weight. I'm looking at this. All right. Then you ask yourself, based on the application I'm working on, which is more important? If you are working with a fridge, thermal insulation is more important to me than the weight. Yes, I want it to be lightweight. Okay, but thermal insulation is more important to me. And so I will give it a higher weighting factor. And then I compare all my materials and I select objectively the material that is the best based on my criteria. Is that okay? Based on my criteria. So that is the decision matrix, one of the most powerful, a very powerful, I don't know whether it's the most, a very powerful tool in selecting which idea is the best. Okay? All right. I'm going to stop sharing my screen and go back to the slide. Any questions? Romanus was raising his hand at some point. Romanus, do you still have that question in your heart to ask?
Hello, sir. It's not Romanus, it's Emmanuel.
Okay, was it Emmanuel?
Okay.
Yeah.
Yes, sir. So I just wanted to get a clear understanding about this weighting factor.
Okay.
What does it entail? The weighting factor entirely.
Weighting factor, like I've explained already, right, is dependent on what is most important to you. And I've used the cooling system, for example. Okay. In a cooling system, I want that if I have worked hard to cool the chamber, it should stay cool. Okay? There should be no heat transfer across its boundary. And so whatever material I'm using to make the chamber, it should be a material that has high thermal resistivity, very high. That is more important to me than how heavy my fridge is going to be. Are you following me? So for me, based on that, yes, I want a fridge that is lightweight, that can easily move around. But also, what is more important to me is that I want the fridge to keep cool when it has cooled its chamber. And so I will give it higher marks. Assume it like marks. So I have a total of 1 marks that I need to share. Or if you don't want to use one, you can use percentages. Okay, you can use 100%. I have 100% that I'm going to share amongst all my criteria. So I will share it based on which one is most important to me. If it's not important at all, it will not be here. So you can't give it a 0. All right. They are all here because they're important, but others are more important. And so I will give thermal conductivity a higher value. Maybe I'll give it 0.4 or 40%. And then I will give weight. Weight is also important, but it's not that important. I may give it 10%. Okay, assuming that there are other factors that we need to share the other percentages amongst. That's how the weighting factor works. Is that okay? All right, Lute. Lute's hand is up. Can you now speak?
My question goes back to when you made mention of the design, like the conceptual design, when you made mention of team collaboration. So my question was, how about situations when a person, like, it is just an individual person, just a single person that has the idea? How will he be able to, like, make the others understand what he himself understands? Like his own team that is working with understands, and the both of them are able to create the same, like, solutions or proper solutions to the problem.
Okay, what you want is not that all of you will have the same solutions. In fact, that's why we say at the concept generation stage, you want many different solutions so that the solution that eventually works did not only work because that was the only solution that you could think of. If you are alone generating the idea, it's okay, right? But it's just that the robustness of that idea will not be as when you had other people. Okay, so when you have that idea and you have a team you will need to present, that's why we do presentations and pitches. You will come and you say, look, the problem we want to solve is this. This is our aim. And based on this, I have thought through. That's where you can even provide, what's it called now? A roadmap of the various ideas you thought through. Because we wanted something that is this, and this at the same time. I first thought of this, but it didn't have that. Then I thought of this, it didn't have this, but this one has both this, and this. Even though there's one problem like this, but I'm feeling that the problem he has is not very significant compared to the advantages. So holistically, this, that. So it's left for you to explain. And if the people say, no, that other one is better. You said this. That's the essence of having more than one person on the team. Did you actually consider this? If you did, you say, yes, I considered it, but that was different. It's not all the time that people will agree. People will disagree. For example, now, I'm saying that thermal conductivity is more important to me. Another person say, no, I prefer weight. I want it to be lightweight. What is thermal conductivity? Say the fridge will always be working. So it's left for us to be objective. And that's why I said at the beginning that when you are doing this, it's not about sentiments. Some people just love their own opinion. They don't want anybody to put it down. So when they don't take your opinion, you now feel bad. You start getting angry with everybody. You now refuse to take other people's. No, we are working towards the same goal. Explain yourself. If you don't agree, no problem. That's fine. You don't agree, but no problem. Now, why don't you agree? Let's see. Maybe you can win me over.
Yeah,
Give us your
like
reasons.
that watching.
Do you understand?
Yes, sir.
So, somebody's mic is unmuted and they're talking in the background. Maybe I should stop all of you from being able to unmute. Okay. It was Lute that asked that question, right? Are you happy with that?
Yes, sir.
All right.
Yes,
Thank you
sir.
very much. Great. So we were at the decision matrix stage. And once you select your product, the next thing is your detailed design analysis stage. What's the time? 10:30. Wow, I need to rush and finish now because I have something else to do. So based on the best solution that you have now selected, you are now going to use your knowledge of engineering sciences and mathematics to determine the sizes of the components, to determine the acceptable values of various parameters. You will generate mathematical models that will represent the behavior of that thing, okay? So that you can work with it, you can check, okay, what if temperatures get like this? What is going to happen with this? You simulate. Okay, that is what you do in the detailed design and analysis stage. Okay, the generated mathematical models, you can now simulate them to understand how the system will behave. If the system is behaving how you don't like, then you go back and tweak. That's the essence. So that you don't go and build a model, build another one, and waste money and materials, and you destroy, build, and it didn't work. No, that's what simulation is for. This thing is going to carry this amount of load. This thing is going to operate in an environment that gets as high as, let's say, 40 degrees Celsius or 42, 43. Let's test. If the ambient temperature is 42, how much heat gets into my cool chamber? Then you run a thermal analysis to see the heat flow rate across that. You see what happens after so hours. What is now the temperature of the something inside and the temperature of the one outside and all of that. So you gain understanding. So that's what happens. And before, in fact, not even before, even now, all that we're going to do in this class, in machine design 2 in 500 level first semester, machine design 3 in 500 level second semester, is based on this. You are going to be, oh no, my battery is almost gone, so I must run now and finish. It's based on trying to determine the correct sizes. So when we start looking at shafts, designing shafts, we are trying to say what should be the correct size and shape of your shaft to transmit a given load and a given power. When we come to designing bearings, all the machine elements that we will design is all based on determining the sizes of the components, the material type, and all of that to avoid failure. That's what we're going to do throughout machine design, starting from now till 500 level. Is that okay? Communication. Okay, we talked about this, right? Continuous communication is very key. You must communicate with every stakeholder in the project to ensure that they are satisfied. If the people you are designing this thing for, you are not designing it for yourself. You are designing it for a market. They must be. That's why when you finish, you do test runs. You give people to try your product out and give you feedback. You will keep communicating. Sometimes before people build something, they go and ask them, if you were to have a fridge that was not using electricity, what do you think it would be like? What will you look out for? They say, I want something that's like this. I want some communication. Okay. Where there is no communication, you would have wasted efforts, wasted designs. Sometimes you have generated a very great design, but because you did not, put it together properly, you can't get funding. It's solving the problem, but to mass produce, somebody must sponsor it. You go and pitch your design to people. Is that okay? You might have inventions that are lost. Now, 3 forms of communication: oral, written, graphical. Because of my battery, I'm running, right? Oral is good, but it's the least robust of all of this. Graphical is the most robust because it doesn't depend on a particular, in fact, it's a universal language. Okay? And it involves using sketches, drawings, visual aids, computer graphics, and models to transmit an idea. Is that okay? To transmit an idea. Computer-aided drafting is critical for us because you must, when you have thought up and conceptualized a solution, you must be able to present it. And when you use computer-aided drafting, you increase the accuracy. There are a lot of advantages. I don't have time to talk about them now. So we deal with graphical communication in engineering. By the time All right, sorry about that. I will plug my laptop now so that I'm not having to rush tomorrow, but we'll soon be done. So graphical communication is important. When you come to 500 level, second semester, I'll teach you computer-aided design, but I'll be focusing on the use of Autodesk Inventor for this. Okay, it's not just a drafting software, it's a design software. If I have time then, some of the calculations we will do now, I will show you how to achieve them just by simple clicks. The software already does those calculations for you, right? But we'll have to learn the procedure manually at this stage. It's all right. So graphical communication is very, very important for us. Thank you. I think it's tragic. So what's the next? The next step is prototyping, right? After you have done you have conceptualized your solution, you've carried out detailed design analysis and calculations to determine sizing. You now use those sizing and your concept to now generate models, 3D models, 2D models, working drawings. You carry those drawings, you go and do a presentation pitch, right? And someone says, that's a great idea. Can we see a physical prototype? This is where you now build. Okay, you create a physical model of what you have been working on. All right. Sometimes it's a full-size model, sometimes it's a miniature version of it, a smaller size version, but you are trying to create based on what you have conceptualized, based on what you have created. You can have digital models. Now you create a physical model with which you will operate in the environment and see, does it actually work the way my analysis said it will work? And that's what the evaluation stage is, testing and evaluation. This is where you will rigorously check. You will check your product, you will check your material, your solution. Is it working? What are the problems that are coming up that I never envisaged, that we never thought of? Sometimes until something starts working in real life, you won't know how it behaves. And then you start saying, okay, we didn't think of this thing. Then you go back to your ideation stage and go and tweak something. Okay? When the criteria is not met very well, you go back and you tweak the design. You keep working on the design. And that's why there's what we call research and development. When you first do the proof of concept for a product, we give it about 10 to 15 years. Some people can be using it. And as they're using it, they're giving you feedback and you're improving on it. You are working it until, in fact, before it gets to where people use it, you yourself from your first testing, you will come back and check things and come back again. It took about, was it how long did it take? 5 to 10 years before the Cybertruck eventually came out. The first time Elon Musk and his team showed the Cybertruck, when they were trying to prove that the glass was unshatterable, and then there was a big metal bulb that now shattered the glass. They went back. People had already prepaid for the truck, but they went back and still did a lot of testings and designs and all of that before it was eventually released to the public. It takes a long time to do research and development before your product can be considered safe to be used by huge numbers of persons. Is that okay? And this brings us to the end of the design stage, the design process, I beg your pardon. Okay? You recognize a need, you define the problem, you research around it, then you ideate, generate multiple solutions, and you select the best solution. Then you carry out detailed design analysis and calculations, right? Then you communicate, you give us graphical communication of that design, correct specifications, correct dimensions, correct materials, shape and form. You represent it either digitally on the paper. Then you build a prototype, and then you run several tests on the prototype until it becomes a product that can be commercialized. And that's where we stop for this class. And then questions, when we come next time, we will jump into the design of machine elements. Any question? Okay, I'm seeing questions in the chat. Let me stop sharing my screen so that I can look at. Ideally, what informs the weighting factor? Okay, we've answered that already. What instrument is used in determining weighting factor? Okay, no, it's not a weight. Well, I've explained that already. So you have seen, I'm also seeing the need for market surveying concept selection in order to determine exact market cost. Now, where market survey comes into place, that's part of your research. Okay, remember the stages before you ideate. What's the stage before ideation? Is research. That's when you go to the market. That's when you ask people. That's when you find out prices of things. That's when you check books. You check catalogs. You go and carry company catalogs. How much do you sell 1 millimeter square of rod? All of that. The market survey is embedded. That's what you do with research. Because it's the information and data you get from that feeds into your ideation. All right. I think that's the only question that is in the chat. Any other question? Do we have any other question? Can you hear me?
Yes, sir.
Yes.
Okay. Any other question?
Yes, sir, please. When you talk about the detailed design and analysis, you say we generate mathematical models that represents the real life behavior.
Yeah.
And also when you talked about prototyping, you talked about physical models of the design.
Yeah.
If the mathematical models is already representing real life scenarios, why the physical models are the mathematical models? That's basically my question.
All right. Now, there are different kinds of models, right? And you've heard there are digital, what we call digital models. There are graphical models. What you do in your drawing are graphical models. Okay? They are representing a real life object, that are showing us its form, its shape, its size. Okay? So you have drawing models, and now those drawing models can be digital. Okay, where you see them on a computer, you can interact with them, you can turn them around. When you come for in 500 level, and I'm teaching you Autodesk Inventor, that's what we handle in second semester, right? And then there are mathematical models. The graphical models are based on mathematical rules also, rules of size, rules of projection. But when we talk about mathematical models, we are referring to a mathematical expression that defines the relationship, things that happen in an event. Now, it is a model. In doing those models are hinged on assumptions. You assume this, you assume that, you assume this. You know, all your equations of motion, when you say, okay, if a car is moving with this velocity, right, how long will it take the car to get to this point? And you calculate. That is a mathematical model that describes the motion of the vehicle, that correlates the speed of or the velocity of the vehicle with how long it takes the vehicle to get to a given destination whose distance is known. Is that okay? So mathematical models represent events, behaviors, if you like. Is that okay? So you have equations. When we talk about mathematical models, you see, when you do partial differential equations, all of those things, they teach you how to model. You have wave equation, you have heat equation. These are models that represent what happens when heat is moving. And it's different from your physical. So physically now, we're saying now build a thing. Let's put it in the hot environment. Let's see how heat interacts with it. Then we can know. Your mathematical model is built on assumptions. Okay? It's built on assumptions, and that's why you have errors. Sometimes you will talk about what is the error margin. if it depicts or you can predict what will happen in real life almost accurately, then the error margin is very small. Or it's all built on assumptions. If your assumptions are correct, you have correct values. If your assumptions are wrong, I remember when I was doing my PhD, I worked with micro and nano structures. Okay, and I was trying to find the resonance frequency of a nano bridge of graphene, right? And then I carried vibrational equations and I applied them to them, and it gave me frequencies. But boy, those frequencies were far from what they actually were. And then I discovered that, oh, look, those equations were made for macro structures. If you look at their assumptions, they assume that if you are dealing with a structure that behaves as a continuum, if the structure is rigid, if the structure is this, then those equations will apply. Assumptions. So all those assumptions did not work for me because at a micro and nano level, my structure ceased to be a continuum. It was more like a network. By nano level, you're already seeing the atoms and you're seeing how they are interconnected one with another. So it's not behaving as a continuum anymore. You now have to start applying discrete. So those equations, even though I applied them, they gave me answers, but the answers were completely wrong because the assumptions upon which those mathematical models were made, my physical scenario did not meet them. So I had to now start modifying, start looking for other means of determining the vibrational properties of my micro and nano bridges. Are you following me? So when we say you generate a mathematical model, sometimes it's not even you physically because those things are their computational requirements are very high. Okay? Software will do it for you. You build a model and then your software will generate the model the mathematical model for you and even solve the equations in the background for you. That's why it's computer-aided design. Okay, solutions that you will solve and take weeks to solve, they will solve in a few seconds. All right, thank you very much. Any other question?
Yes, sir.
Okay, go on.
My question is on prototype process. Now, assuming now you have finished your process and you have to make a prototype, that is the trial product.
Yeah.
So what if you make the prototype and it didn't work as you intended it to work? Are you going back to the first process or there is a particular place that you start?
Yes, you go back. You identify. That's the whole essence of creating the prototype. Usually at that stage, you go back to the ideation stage where you're creating the concept. Sometimes you might go back to question your calculations. Maybe it's the calculations when you were sizing components. Maybe there was a component you did not size properly. This thing is failing. Your shaft is cutting. It means that the power your shaft is transmitting or the loads under which it's acting is more than you imagine. So you go back to your calculation stage. In that case, it might not be a conceptualization stage. Not that you go and change your design. No, you come back to your calculation. I didn't calculate this size correctly. What is the size that can withstand this load? So you may need to reassess. So you might jump again now to research and reassess what are the loads acting on this thing. When we come to start doing machine design, I always tell you people, when I come, I'll tell you again. In the classroom, we give you people what we call structured problems. When you come to write exam, you write test, we give you a structured problem. We tell you a shaft is meant to transmit 45 kilowatts of power. Okay, it has 2 gears mounted on it. The first gear is mounted at a distance of 200 millimeters from the leftmost bearing. All of these, then we say determine the size of the shaft. That's a structured problem. It's structured because We have given you all the parameters. We have defined the scenario in which you have to work. You are only carrying out calculation. In real life, problems are not structured. Part of your solution is to structure the problem. So you want to build a machine, you want to build a shaft, and all of that. Nobody is going to be giving you values the way we give you in class. You will determine them yourself. That's where research is. When we are running this kind of business, what are the forces acting? Okay? You might consider some forces and forget to consider others, maybe because of your knowledge base. And that's why you work in teams and you work with experts. Someone say, so far as this thing is rotating, there's another force called this that will be acting on it. And you say, I didn't consider that. You go back and consider it. In real life, problems are not structured. You structure them. And this goes in line with the modeling I was talking about, right? You are the one to determine what is happening, what is interacting with this. How much can I take? You cannot represent 100% what happens in real life in mathematical models. The model will be too large. It will be unsolvable. If you have one equation and you have 5 different unknowns in that equation, you can't solve it. Mathematics tells us that you must have 5 equations, right? 5 different equations about the same thing to be able to find out 5 different unknowns. So you begin to push things aside and do all of those to bring your model down to something that you can solve. So when you have created a prototype and you tested and something failed, you start asking yourself questions. Is the answer to those questions that will determine how far back in the process you will go? Are you going to go back? Maybe you didn't define the need properly, the problem properly, or are you going to go back to the ideation stage? Do you need to change the design, or is it a calculation something? Where you go back to will be determined by the problem you encountered. Is that okay?
Yes, sir.
All right.
Thank you.
God bless you. Any other question? All right. There's no other question. Thank you very much. So next week, if there is a classroom again, I will come to class. If there's no classroom, I will continue like this. Last week's class, we didn't record, but this one, okay, it was control engineering and automation we recorded. I will put both of those on my YouTube channel and send to you guys to watch. By the time exams come, I will take them down. So you have the whole semester to watch it. So when I upload, I will send you the link so that you can always go back to this class. So perhaps what I'm doing online to check it again. All right. If there is no other question, we will bring the class to an end at this point. Is there any other question?
Thank you, sir.
No, sir.
No question, sir.
There's no question. All right. So God bless you. I pray that God will keep all of you this week and that you will learn well. Somebody is still confused on something. We'll talk about your confusion next week. When we come next week, remind us. I'm still confused on the criteria used for design. Still confused on the criteria used to evaluate a design. What do you mean? Who is talking? Can you
John.
Who is asking the question? Who was that?
Sir.
John Godwin.
Like, Godwin John. Yes, sir. Yes, sir.
Yeah, go on.
Like, on the criteria you list, you only showed us the criteria to be used, but you didn't explain, like, in broad detail how we can use those criteria, like how we can pass through those steps based on the criteria you listed, and then in order to evaluate
I
or
showed you.
our
It's not that I
designs, you
didn't
didn't
show
just
you
explain,
all
you
of
just like
them.
brush through.
I showed you. When you come to,
Okay,
if you look at the example of the crane hook, look at those criteria. Is there anyone that talks about manufacturing cost or material cost or cost in general? Yes, there was cost. There's repairability. There's durability. We can't explain all of them. We'll have a long class, and I expect that by now you should understand what each of those are. When we start looking at our design of machine elements, most of our designs are based on strengths. That one you will see it extensively.
Okay, sir.
So we can't take them
Yes,
one by
sir.
one by one, and this semester, next semester will not be enough. All right.
Okay, sir.
God bless you. Thank you very much. And we'll see you guys next week.